Hello, my name is Hannah Day, and this is Lab 3. In the universe, stars interact with black holes that are located at the center of galaxies. This causes stars to have a circular orbit as the gravitational pull from the black hole affects their motion in space. This lab demonstrates how physics principles can be used to prove the existence of black holes by working backwards to identify the unknown cause of observed forces acting on objects in space. I was asked to write a code to compute the motion data for a star orbiting a black hole. I was given the location of the star, the location of the black hole, the mass of the star, and told to neglect other forces besides the black hole acting on the star. The goal is to find the mass of the black hole using the given and computed data. I found the mass of the black hole to be approximately 6.7 times 10 to the 33rd kilograms. And that makes sense based on the mass of the black hole would be very large in space. I was told to first assume that the system is a star near a black hole and assume that the F net is from a single force, which is a gravitational pull from the black hole, where you can assume that there's only one gravitational force pulling the star to the black hole. And I was told to assume that the black hole is located at the origin, which is supported by the origin vector given in the initial code. A few key physics principles for this lab include Newton's second law, which is that the F net is equal to the change in momentum over the change in time, and the universal law of gravitation, which is used to estimate the mass of the black hole, where the force of gravity is equal to a constant g times the two masses divided by the square of the distance between the two. I was told to split the net force into the parallel and perpendicular components, where the F net parallel is equal to the change in momentum over the change in time parallel, and the F net perpendicular is the change in momentum over the change in time for the perpendicular. The initial glow script data provided me with the radius as 3 times 10 to the 11th, the origin vector is 0, 0, 0, and I plugged in the gravitational constant g, which is 6.7 times 10 to the negative 11th, the mass of the star, which was 2 times 10 to the 30th, and I changed the time step delta t from 1 day to 86,400 seconds. Then I had to apply known physics equations to calculate momentum, F net, and parallel and perpendicular components of the net force. To do this, I had to apply Newton's second law, where F net equals the change in momentum over the change in time. So first I had to calculate the initial momentum is the mass of the star times the initial velocity, same process for the final momentum. Then the change in momentum and the change in velocity were both the final minus initial. The dp/dt is the delta p over delta t, and then Newton's second law, which is to calculate F net, which is the dp/dt value as calculated above. Then to calculate the parallel component of the dp/dt, I had to first establish p hat, which is the initial momentum divided by the magnitude of the initial momentum, and then the magnitude had to be found for dp/dt, and then this was used to multiply the magnitude of dp/dt times p hat, and this gave the parallel component of the change in momentum. Newton's second law states that the F net parallel is equal to the change in momentum of the parallel component, and then the perpendicular component was found by taking the total change in momentum minus the parallel component, resulting in the perpendicular, and the F net perpendicular is equal to the change in momentum perpendicular. To calculate the mass of the black hole, I had to rearrange the law of universal gravitation to be the mass is equal to the F net times the square of the radius between the two objects divided by the constant g times the mass of the first object. This can be seen entered in the bottom of the screen, where I first had to define r as the star's position minus the radius of the black hole, which is the origin position. Then I had to scale the arrows to show the forces as applied in the model. I use an arrow scale of 1 times 10 to the negative 17th, and these can be seen in the code as it runs. So you can see that the star begins to speed up as it moves closer to the black hole, and then it slows down as it moves further away. The parallel component of force is the blue arrow, and then you have the perpendicular component as the orange, and the F net is the pink arrow. The results that the glow script calculated was that the F net is about 7.5 times 10 to the 28th, and then this is split into the parallel and perpendicular components as shown. The top value is the approximate mass of the black hole. What does this mean? How are the net force and its parallel and perpendicular components different from the rate of change momentum and its parallel and perpendicular components? An important thing to note is the rate of change momentum is an effect of the net force, but equation-wise, these values are about the same. We have the F net is the change momentum over the change in time. So taking time into consideration, these two are a reflection of each other. This on the right here is a breakdown of dp dt into the parallel and perpendicular components. The parallel component is non-zero if the speed is changing, and it's equal to the F net parallel, and the perpendicular component of the change momentum is non-zero if the direction of the object is changing, and is equal to the F net perpendicular. Then what if? The black hole of a known mass was removed and replaced with a different black hole. Assume that the motion of the observed star remains the same, except it is now affected by the gravitational force of the new black hole. Would you be able to tell the difference? No, I would not be able to tell the difference, because if the mass of the star is the same, and the position of the star and black hole are the same, the motion would look the same and thus make the calculations for a new black hole's mass the same as calculated in this lab. This is true of a process where you are using the observed forces to calculate the cause. This has been Lab 3. Thank you so much.